solve it here. So I've got the problem over on the right hand side, and I'm gonna go through it, take all the information we need. So I've got a diagram there. We can read it first. Determine the largest load P that can be applied at A when theta equals 60 degrees if you know that the average shear stress in the 10 millimeter diameter pin at B must not exceed 120 megapascals, and that the average bearing stress in member AB and in the bracket at B must not exceed 90 megapascals. So I want to bring some of this given information over, and I want to sketch this out. Call that point B. Call that point A. Bring this guy down. That point C. And let's call this P max. What else is given to us? All right, we know that this is 750 millimeters, and this is 750. Then we have some dimensions of the components. I got the two 750s. I need the angle. Theta is 60 degrees. 60 degrees right there. We have some more information. The width of AB is equal to, it's 50 millimeters wide right there. And the thickness of AB that's equal to 16 millimeters. And then the bracket at B the thickness of the bracket is equal to 12 millimeters, and there's two of them, times 2, and we observe that this pin that connects the bracket and the member AB is in double shear. There's two shear planes. We are given sigma allowable, or sigma max, the maximum allowable normal stress or bearing stress in AB is 90 megapascals. And sigma, not sigma tau, that doesn't work anymore. Pushing that button, so I can do that. Tau max, the maximum shear stress in the pin is equal to 120 megapascals. So this really has to be done in two parts. There's two distinct parts. One, there's an internal force. This is this member AB is really a two-force member. It's got a pin here, right? It's got a pin. There's two different forces acting on it at the top, P and something from this yellow string or tension cord, but those can be resolved into one force here, and they have to act along the centroid of the member, because you've only got a pin at the other side. Required. So that internal force has to go through this pin into the bracket. We got to check the pin, and then we have to check the pin bearing against the bracket with the two ears at the bottom, and check the pin bearing against the member AB. So in one case, here is the pin, and it's going to bear against that hole in member AB, and in the other case, here is the pin, and draw this one a little more carefully. It's going to bear try to draw a concentric circle, concentric with the center of the pin. And this comes down, and then this comes over, and this comes down. It's going to bear against the bracket here on both sides. The bracket closer to us here, and the bracket farther away from us over there. So I say there's two parts. One of them, we have to figure out how P and FAB, the force in AB, are related to each other, right? And the other one is to figure out what the allowable force in AB is. And it doesn't really matter which way you do it. But let's start with the with the mechanics of materials part of the problem. We know something about tau, the shear stress. It's equal to P over A. In this case here, the P is the force going through the pin, and that is going to be the force in AB. And so I want to rearrange this and solve for this in terms of the force in AB. So there's my generic equation. Always try and start with that. Maybe we'll do one more step. Over the area in shear. I'll just put SH. So FAB is equal to tau max times the area in shear. And really that's the maximum force that's allowed, because the shear stress can't exceed that. So we got to say that FAB is less than this amount here, which is equal to 120 megapascals times the area and shear, and the area and shear is going to be the cross-sectional area of this, and it's going to be times 2 because there's a shear plane here and there's a shear plane here. So I'm going to say 2 times pi, the radius, I guess I didn't put that in my given up here, the diameter of the pin. Oh, it's not given in the diagram. I was searching the diagram. It's 10 millimeters. It's given in the problem statement down here. Pi, so you got to either use r squared or d squared over 4. We can use 10 millimeters squared over 4. And again, we got megapascals and millimeters squared, so we probably want to express our stress in terms of newtons and meters, or newtons and millimeters, or kilonewtons and meters, because we want the units of area underneath to disappear and be left with the force. So that's going to be 120 newtons per millimeter squared times 2 over 4 is 1/2, so we can say pi 100 millimeters squared, that's 10 squared, 10 millimeters squared is 100 millimeters squared, over 2, and we get that equal to, let's grab my calculator, I got 120 times pi times 100 over 2 is 50. I got 18,849 on my calculator, and then some other numbers. I'm going to call it 18,850. And that's in newtons, 18,850 newtons, but it's a big number, so it makes sense that I would move the decimal over here and call it kilonewtons. So that's the maximum force in member AB that's allowed due to the shear strength of the pin. I'm going to color it in again just to highlight. Due to the shear strength of the pin. But we've got a couple other things to check here. It says, you know, the bearing stress must not exceed 90 megapascals in member AB and in the bracket. And so we have an equation, sigma equals P over TD for bearing stress from the textbook. That's the force over the thickness of the material times the diameter of the bolt or rivet that is bearing against the members. And so once again, P here is FAB, and T is the thickness, D is the diameter. And so I can rearrange that FAB has to be less than or equal to sigma max times the thickness times d, which let's get rid of that. Let's do this. 4, we got member AB and bracket at B. So let's say 4 member AB FAB is less than or equal to 90 megapascals. But we're getting the hang of things, so we know that that's newtons per millimeter squared. Same thing. Times the thickness of the material. Well, the thickness is given here, 16. Times the diameter of the pin. The diameter of the pin was given down here, 10 millimeters. And that equals 90 times 16 times 10 is 14,400, or 14.4 kilonewtons. And if we want, I can clean up a little bit here. We don't need that decimal. I got some marks over here I was just showing to try and explain the problem. And then 4, let me do this. So that 14.4 kilonewtons means that's the most force that can go like that against member AB. Now for the bracket, at AB, at B, FAB is going to be less than or equal to 90 newtons per millimeter squared. And now the thickness of that is the 12. And the diameter of the pin is the same. But that would just be if AB was connected to one of these ears. That number would apply. But it's connected to 2 ears, so it's twice that area. So I got to multiply that times 2. And that equals, well, we got 90 times 160 in the one above to give us 14.4, and this is going to be 90 times 120 times 2, or 90 times 240. It's going to be a bigger number than the 14.4. We almost don't need to calculate it because we got to take the smallest value, but I will. 120, 240 times 90 gives me 21,600 newtons. I'll call it 21.6 kilonewtons. So just given these 3 design constraints, the shear in the pin and the bearing stress in AB and the bearing stress on bracket at B, the internal force in AB, the force transmitted from A to B, can't be higher than the smallest number here. Another way to say that is the bearing stress in member AB controls. This here is the one that we need to use, 14.4. Internal force in AB can't exceed that. And that 21.6, I'll point out, that would be, here is the pin. The pin can't push against the bracket any more than 21.6 in order not to exceed the maximum bearing stress of 90 megapascals. But again, the 14.4 controls. And you know what? I jumped right into solution here. I've got my generic equations and rewritten for this one here. So required has to be P max. So I think we're on to the second part of the problem, which you can do first if you want, where we have to somehow relate this force, P max, to the internal force in AB. And really, you need to draw a free body diagram of point A and draw in the forces. And again, if you don't know, you assume tension, and then if it's positive, it's tension. If it's negative, it's compression. On problems that you're pretty confident on, this one here, when I apply that red force P, the yellow string is going to go into tension, so I'll draw that away. We haven't really talked about that at all, but that's going to be the force in AC. This is going to be P max. And AB is going to go into compression. And that's going to push like this here. You know, and depending on the geometry, this is just one position shown here. If you were doing this analysis, not only do you have to analyze other parts of it, besides these three things that we're looking at, you also have to analyze other positions. But for this position, there's a relationship between Pmax and FAB, and in order to solve this, it's a point in space, so we're not going to use any moment equations. But we still need some geometry in terms of angles. And so I think I would come over here and say FAB, here's FAB. I'm just taking this one vector off my free body diagram. I don't want to clutter my free body diagram, but I need to know more about it. And if AB goes up at 60 degrees like that, then it's also 60 degrees off a horizontal there. So I'll bring that across, put in my 60 degrees, and if I'm really being careful, I like to draw in then, this is FAB, but it's comprised of components. It has a component like this, which is FAB in the X, which is FAB times the cosine of, I don't like that color too much, but the cosine of 60 degrees. And this here sorry about that, that looks pretty bad, but FAB sine 60. Right. The black vector FAB can also be represented with two mutually perpendicular vectors, the vector in the x and the vector in the y, just like a three-dimensional could be represented by three mutually perpendicular vectors, the x, y, and z component. And there's my two components. And now I want to do the same thing with FAC, which we have drawn like this. In our free body diagram. And I'd like to know how much it is off the horizontal or the vertical. Either one will allow me to calculate the components in the x and the y. And so I need to think about this problem a little bit, and I think the thought process goes like this. Looking back at this diagram up here, I'll sketch it again quick. I don't want to mess that one all up. But this is 750, and this is 750. This is 60 degrees. And so this angle in between them is 120 degrees. This is a C, and we know that this is 60 degrees here, but I'm interested in AC, and I think the way to do that would be law of sines, say that the sine of this angle over 750 is equal to the sine of this angle over 750. And so the sine of one angle, you have two equivalent, I don't want to write it all out, but those two angles have to be the same because these two sides are the same, right? They have to be the same, and this triangle, the internal angles have to add up to 180, just like this. This has to add up to 180. So if this is 120, I need 180, I need 60 more, and half of it has to go here, and half of it has to go here. And so that limit tells me that this is 30 degrees. So it's a little tricky there, but this is 30 degrees. All right, and that up. Now I want to draw the components of that so I can do my statics. The components are going to be FAC in the x and FAC in the y. The x is going to be FAC cosine 30, and the y is going to be FAC times the sine of 30. There's other ways to do this. You could have taken that triangle that I just drew and created a forced triangle from it, or you could have used the law of cosines and sines on that a little bit more, replacing the 750 with FAB. But this is the way I like to do it. Good old-fashioned statics way approach. Go back to black. No moments, so we'll sum forces in the x, and they have to be equal to 0. and then the x in the positive direction. I have a portion of FAC going to the right. I look over at my little diagram on the side. I have FAC cosine 30. I'll do a little shorthand now. It's going to the right. P max is straight up and down, so it's not in this equation. And then going to the left, I have FAB cosine 60. And that equals 0. So I have a relationship between the two internal forces, the one in member AB and the one in the string AC. And now I'll sum forces in Y. I got P going down, so I'm going to go down positive. And I'll say P max. Anything else going down? Sum of FAC, so I'll add that to it. That's right over here. FAC sine 30. Oh, I was using shorthand here. FAC sine 30. Is also going down, so it's positive. And then going up, which would be negative now, would be a portion of FAB, which is sine 60. That's this guy right here. Equals 0. So just remember back, we're trying to relate P max to FAB. All these numbers were the maximum forces in AB to meet the design requirements and the stress limits that are provided. And so in order to get a relationship between P max and FAB, I got to get the second equation to be just P max and FAB. So I'll write the first equation in terms of FAC. That is equal to, bring FAB to the other side. The cosine 60 comes with it, and I'll divide by cosine 30 to get FAC alone. And then I will substitute that into the second equation. P max equals FAC, which is FAB, cosine 60, cosine, let me fix that, I said the wrong thing, I started to write the wrong thing. Cosine 30, this is why we use pencils. And all of that is this right here. And it's going in right here, so that's multiplied by times sine 30. And where am I at? This is P max plus this. I'll do it in two steps. This is P max plus FAC, which is this, times sine 30, it's here, minus FAB sine 60. Let's put some brackets in here. Brackets. Minus equals 0. So here's the next step. P max is equal to, I'll bring this FAB over, and that's it's now positive over there, sine 60. And And then I'll bring this one with the 3 trig functions in it. You could change that cosine 60 times tan 30, sine over cosine, but we just need to get what this number is. So I'm going to subtract all that off. I'll pull the FAB out, so it's going to be sine 60 minus cosine 60 over cosine 30 times this sine of 30. And I'll finish this out with one more bracket, and I'll show that one is a little bigger there. P max is equal to sine 30 over cosine 30 is 30 tangent times cosine 60 is that number. I got 0.2886 on my calculator. I'll make it negative and I'll add it to sine 60, and I got 0.57735, 0.577 FAB. So P max is equal to 0.57735. If you want to use 4, we put that in there, times FAB, the force in member AB, and therefore P max has got to be less than or equal to, taking the 14.4 kilonewtons, because it's the minimum value, multiplying it times this 57735, and I get 8.313 8.31 kilonewtons. And I'll box the answer. Equals question mark, and I think that's it. Alright, I hope this helps you to understand the problem and get this one complete.